Okay, so in chapter 11.5, we talk about graphing equations. We're talking about graphing equations that are a little more complicated than we've graphed up to this point. So just as a bit of a summary, let's look at an equation for a line we had here, and we can talk about how we graphed it. We might start by setting up a table. So, for example, when x equals 0, y equals 2. So you stick 0 in here for x. 0 times 3 is 0, plus 2y equals 2. When x equals 1, y equals 5. When x equals 2, we've got 2 times 3 is 6, plus 2 is 8. Y equals 8. Let's do a negative number. When x equals minus 1, just to see what happens here, this is minus 3, plus 2 is y equals minus 1. And I'll write the equation that I used out real quick there. Go ahead and draw a Cartesian axis system, xy axis. Notice the spacing on the x is wider than the spacing on the y, because I'm going to need more space on the y-axis than I am on the x-axis, and this will look prettier this way. So let's go ahead and graph our first point, 0, 2. Well, this is 0, the center, and then positive 2 up here. So this is our first point. Our second point is 1, 5, 1, 5. So our second point. Third point is 2, 8, 2, 8. And this should all be creating a straight line because this is an equation for a line. Our last point is minus 1. Minus 1 is down here. I could then go and draw a straight line through this. And any point I pick for x, like say 3/2 or 1.5 here, it would produce a y value that ended up on this line. Okay, so what we're going to do now is we're going to graph more complicated equations. So I could set up a little more complicated equation. Maybe it's associated with how a cannonball flies after fired from a cannon. So suppose I fire a cannonball, and I know that the trajectory follows this equation. Y equals minus the quantity x minus 2 squared plus 4. It's kind of complicated, but we'll see. We'll handle it the same way, and I don't think it's going to be too bad. Same way we did the line above. And I'm going to ask these questions. How far will the ball fly before striking the ground? How high will the ball fly? Well, if we can plot the trajectory, we might be able to figure that stuff out. Okay, so here I put in a Cartesian axis now. And for reference, I redrew our equation down here. And let's just do the same thing we did before. Let's just set a table up and start putting in values. Well, let's first assume that our cannon is located at the point 0, 0. So here on our Cartesian coordinate, I've just put a cannon here, a little image of a cannon here at the 0, 0 point. So this point where this cannon is located is 0, 0. I've only got the positive y scale and the positive x scale here. And let's see how the trajectory of this thing looks. So when x equals 0, here I've scooted everything over so I could write the equation next to this. So when x equals 0, y equals 0. Okay? When x equals 1, y equals 3. Following this equation, y equals minus quantity 1 minus 2 squared, and 1 minus 2 is negative 1. Negative 1 squared is 1. But then the whole quantity is multiplied by a negative, so we've got negative 1 plus 4 is 3. Okay. When x equals 2 then, keep the colors the same, x equals 2, we get this relationship, and y equals 4, because minus 0 plus 4 equals 4. And then I will let you work out these next ones. when x equals 3, y equals 3, and then when x equals 4, y equals 0, and that's enough for now. So I can go ahead and plot these points. First point is 0, 0 here. We have plotted already. Second point is 1, 3. That's this point here. Third point is 2, 4. It's this point here. Then we have, so this will be 2, 4. Then we have 3, the point 3, 3. And finally, the point 4, 0 over here. So our cannonball follows what we call a parabola shape and fires up here and then comes back down and strikes the ground. So now we can answer our questions. First question was, how far will the ball fly before striking the ground? And it looks like the distance here is, let's go with orange. Looks like the distance here is this distance right here, which is 4. So the answer to the first question is 4. Maybe these are miles. I didn't give a distance actually. Now the next question was how high would the ball fly? Well, you would have to figure out what the center point here is, and this actually does turn out to be the center point. You maybe would want to do a couple points to the left or right of this to see if it goes up or down, just to make sure, but just to make a long story short, this is the center point here, and so the highest that it flies is the height of this y value, which is also, by coincidence, 4. And that's the answer to the question. Okay, let's look at a different type of equation. From February 1st to March 6th of this year, the number of COVID-19 cases outside of China followed the following equation. So the way we would describe this is 91.8 times e raised to the power of 0.1377 times x. So this 0.1377 times x is in the exponent. I can rewrite this equation. E is an irrational number, so it's just a number, kind of like pi, only this number is 2.718, and then it goes on forever. I'm just going to estimate it as 2.718 here. So this is the relationship we want to look at and maybe discuss some ideas concerning it. So equations like this, where the independent variable is in the exponent, these are called exponential equations. And they have a very distinct look to them. This is an exponential growth equation. It has a very distinct look to it. And let's plot it, and we'll see what that looks like. So here, when x equals 1, y equals 91.8 times 2.718 raised to the power of 0.377 times 1. Let's do that in the calculator. Here, I'll type in 91.8 times 2.718. That's interesting because that's my estimate for e, but here in the calculator I could actually press this exp. That's it's gonna be the same thing. Now this is raised to the power, so that's what that little caret will do when I do this x to the y, raised to the power of 0.1377 times 1. I'm not going to do that, but this equals 105.35, 1 something something. I'm just going to round to the nearest person because we can't really have a portion of a person. So y is over here. It won't. Okay, now putting in x equals 2 up here in the exponent. And I typed in 91.8 times 2.718 raised to the power. Now I had to use parentheses here because I wanted to make sure that this was all kept in the exponent. And I had 0.1377 times 2. And I press equal. And now it's grown to 120.9. I'll just mark that as 121 people. Here I've done the calculation for 20 days, for the 20-day mark of and the number of infected people outside of China was around 1,441 by the close to the end of February. Actually, February had 29 days this year, but on the 28th of February, if I put 28 in this equation, I didn't do these two, then 4,336, and finally, the 40th day, which is equal to March 10th. I think I said the 6th up above, but let's go with the 10th, is 22,630. So let's go ahead and plot this. So I've set up an X and a Y axis over here. Here's my X, here's my Y. Along the X axis, I put the number of days. There's 40 total days that I'm taking into account here. So this is February 10th, February 20th. By the time we get to day 30, that's actually March 2nd. And day 40 is March 10. So let's go ahead and put these numbers in. So for 1, we had, okay, and then along the y-axis, the scale is much different. I have this broken into 5K spaces, so 5K, 10K, 15K, 20K, 25K. And so at 1 here, we had 105, that's pretty low. That's down here. At 2, the same deal. Down here. At 10, we have 342, which pretty much is still down there. At 20, we have 1,441, so that's about right here. So it's slowly moving up. So it looks like almost a line going here. By the 28th, though, we have almost 5,000. Now it's curving up rapidly. And by the 40th, we have 22,000. And that's up here. 22,000. So this is the point 40, comma, 22,630. Scooch this over just a tad. Okay, so with exponential growth, you get a curve that starts out shallow and then it grows really fast, like this. So this is a plot that sort of models the number of cases outside China in the month of, essentially over the month of February and the beginning of March.